So, Mr. Reed, A, circle the line where the object is moving the fastest. Would that be line 1, 2, 3, or 4?
4.
Whoa, Mr. Reed. Remember, this doesn't have necessarily, this is not like a negative value. This just means that it's moving back home. So, hold up, Mr. Reed. Which one can you eliminate? Line 1, 2, 3, or 4? You can eliminate which one? I agree. You can eliminate 2, right? Because it's 0. It's at rest. So now we're down to line 1, 3, or 4. So
It's 1.
they kind of look like they're going the same speed. What are we looking at? What are you looking at? How are you determining? We're not doing math right now. What are you looking at to determine it? The slope. I agree. And we can definitely do the math on that to determine the slope. I agree 100%. So let's look at this one. We've got this slope. We've got this slope. Yeah, we've got this slope over here. If we had to make a determination of which one is moving the fastest, it sounds like Emily is dying to answer the question. Emily, are you right or are you wrong? Which one is it?
I think it's
Number
number 4.
4 is the correct answer.
Because of the number of boxes.
That it's going through in that certain amount
Well,
of time.
there's 2 boxes in a longer distance than the 2 boxes in line number 1.
Correct. Correct. And then part B says, put a star on the line where the object's moving the least. The least. And so I get students who get this on the quiz wrong or on the test wrong all the time. And I'm asking New Julian, which line would that be? Line 1, line 2, line 3, line 4?
Did you just say new, Julian?
Yeah, new versus old.
There's 2 Julian? I thought you said Julia.
Oh, sorry, Julian.
I'm going to say 2.
I agree 100%. So I have students that get this incorrect because put a star on the line where the object is moving the least. 0 is as least as you can go. 0. Okay? Let's keep going. Now we've got, let's look at this. DT graphs can be nice, pretty slope lines. But DT graphs can be curved lines as well. Okay? So what's happening on the DT graphs over here? When I have a curved line on a DT graph, that means that the speed of the object is changing. The speed is changing. Those other nice, pretty straight lines were consistent speeds that were exactly the same, and it wasn't speeding up and it wasn't slowing down. Here, the object's speeding up and it's changing its speed, and that's where that curve comes into place. Turn the page.
Using new colors, Wisconsin.
I don't know if we're going to get there or not. I'm hoping we do. Yeah. Oh, I changed the color. I'm sorry. Acceleration. So let's talk about acceleration now. Okay? We talked about speed. We talked about velocity. Now we're talking about acceleration. It says here, though, look at the following data. Describe the object's motion. So here's the data. Let's look at the motion. The time always starts at 0, and it went to 1, 2, 3, 4, 5. Hopefully we all agree that time can only be positive, it can never be negative. Velocity, which is a a vector quantity, 0 to 10, 10 to 20, 20 to 30, 30 to 40, 40 to 50. This time, from here to here, is increased by 1 second. The next section, increased by 1 second. The next one, increased by 1 second. And it continues. When I look over here on this side, I can see from 0 to 10, my velocity increases by 10 meters per second. From 10 to 20, it increases by 10 meters per second. 20 to 30, it increases by 10 meters per second. So when describing the object's motion here, I can say that there is an increase in speed, my abbreviation is SP, of 10 meters per second for every second that it is moving. That's important. One more time. When I look at this VT information, this acceleration, I see that my object's velocity is increasing 10 meters per second for every second that it's moving. Because of that, acceleration ends up, because of this definition or information, it actually comes out to be a weird SI unit. It's actually, I'll go back in a moment. Acceleration's SI unit is meters per second, or abbreviated as meters per second squared. Or it could be shown as kilometers per hour per second. Or it could be miles per hour per second. Weird. Because, one more time, when I look at this data shows me that my object's increasing 10 meters per second for every second that it's moving. In the table to the right, the velocity is my velocity increasing or decreasing? It's increasing, I agree. Acceleration is defined as a change in velocity. Remember though, velocity can change if an object changes its position, or velocity is a vector quantity, so its position or direction. And so, because acceleration has velocity in it, then that means that because velocity is a vector quantity, acceleration, because of association, is also going to be a vector quantity. Acceleration occurs when an object is increasing the rate of change in velocity in a given time interval. Now, we do have a few other weird things. One thing is called constant acceleration, which occurs when an object changes its velocity by the same amount each second, just like in my example over here. This is constant acceleration. Don't confuse this constant velocity though. If an object is changing its velocity, whether it's by a constant amount or a varying amount, it is an acceleration or it is accelerating. An object with a constant velocity is not accelerating. Okay, so confusing, that little paragraph right there from the book. Let me simplify it.
Will you write it down?
Well, okay, sorry.
A lot of writing.
Can I give this one a summarizing it?
Okay, give me
Okay.
your,
So when you drop something, it increases its speed, right? The longer it falls. But an object with a constant velocity is not accelerating. That's like driving down the road with cruise control.
with cruise control, absolutely. Is it accelerating? No, it's not. But does it mean, is it moving?
Yes.
Yes,
that
it is.
rest?
Nope, no, we just,
Wait.
okay, so hold on,
Over
let me,
here.
we're on a new topic though.
But it's
Nope, that's DT. We're not on speed anymore. There are 3 ways to change acceleration. I'm going to shortcut this for you. Number 1, speed up. Number 2, slow down. Number 3, change direction. So, let me give a couple of examples. You could be speeding up, going faster in your car. You are considered to be accelerating. You're in your car, you come to a stop sign, you slow down, come to a complete stop, you are accelerating. You've got cruise control on in your car and you're moving at a constant 25 miles per hour slow. You've got your cruise control on slow. And there's a curve turn up ahead, you never take off your cruise control, you leave the cruise control on, and you turn directions with cruise control on, you are accelerating, even though you are maintaining the same exact speed. You are accelerating because you change directions. So this right here is going to simplify it for you. One more time. 3 ways to change acceleration. Speed up, slow down, or change directions, even if you are moving at a constant speed. Here are 3 data charts for us to look at. Data chart number 1, my time. What's going on with the time? It's increasing always. But what's happening with my velocity? From 0 to 1, it increased by 1. From 1 to 4, it increased by 3. From 4 to 5, it increased by 1. So looking at data charts with velocity and time are acceleration. And so we need to break it down to see what's going on. It increases by 2. What's going on with my data chart is that it's accelerating. It is accelerating. Let's look at let's look at data chart number 2. Again, time is only can go in the positive direction. So look at this. It's increasing. But my velocity from 0 to 4, it changed by 4. 4 to 8, it changed by 4. 8 to 12, it changed by 4. 12 to 16, it changed by 4. Well, this is what we call constant acceleration. But numerically, it has a 0 answer. And I'm going to go ahead, this is meters per second, and this is second square. It has a 0 as an answer, but it does not mean that it's not moving. It is moving, but it is not accelerating. And so students get confused. It's not accelerating, so it's 0 for the acceleration number. But when you look at the velocity number, it is moving, but it's moving at a constant speed. Next one. Forgive me. Toss me that in the whiteout. I meant to say all of that on this side. Forgive me. Again, time is increasing. 2 to 2, the change was 0. 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 This is constantly accelerating. It's getting faster by a constant number. This one, though, it is moving. It's not getting faster. It's not getting slower. There is no acceleration, forgive me, which equals 0 meters per second square as an actual number. But yes, it's moving. It is moving, but it's not accelerating. This one is moving, and it is accelerating constantly by 4, 4, 4, 4, 4. It is getting faster. And remember, it also could be going slower as well. Acceleration is a vector quantity, so that means that it has direction associated with it. The equation for acceleration is acceleration equals final velocity, final first, minus initial velocity over time. Or abbreviated by A equals V sub F minus V sub I over T. And a lowercase a in physics stands for acceleration. A, lowercase v sub f stands for final velocity. A lowercase v sub I stands for initial.
What's an uppercase T in physics?
Temperature. I had to stop and think. A lowercase t stands for time. In the units, which are odd, are meters per second, which we abbreviated or changed it to meters per second square. Or you can have a combination of kilometers per hour per second, miles per hour per second. You can have some pretty weird ones. But usually we use meters per second square, especially in this class. But I'm not saying that those are not correct. They are correct also. If a toy speeds up 2 meters per second for every second, its acceleration is 2 meters per second, or written as 2 meters per second squared. This is what we're accustomed to using. This is also correct. Hint, hint, quiz/test. So if you see any of those or this, they mean the same thing. There is one more page that we need to get to before we get to the coloring, and then we don't even have to color today. We can be done if you want to.
Yes.
So we have homework on Friday. Homework 2? Okay, we're going to color today. Here we go. Let's take a look.
More than 10 minutes. We have like 12 minutes.
Oh, we have 12 minutes? Oh, okay, so we'll just do this page. Example, I'm going to skip to example number 2. On example 2, a shuttle bus slows to a stop with an average acceleration of, whoa, there's a negative number. It does not mean a negative value. It means a negative direction. Also though, in physics, for acceleration, negative accelerations means slowing down. One more time. I understand that negatives mean a direction in physics. But in physics, when we're talking about a negative acceleration means that the object is slowing down. And what does it say? That it slows down to a stop with an average acceleration of negative 1.8 meters per second. How long does it take, question mark T, for the bus to slow from 9 meters per second to stop? This is my V sub I, and my stop is my V sub F. Julia, give me a number for stop. Say it again. I want like an actual number. Stop. Thank you. So this is a really good practice question now. So give me a few more minutes, please, because in physics, words have number value. You have to read the words, read the sentences, and then from there you have to decipher the, craziness and actually pull the numbers out of it. I'm coming to a stop. What is the speed of that stop? 0. So that actually means a number of 0. Let's go ahead and acceleration equals final velocity, final first, minus initial velocity over t. My final velocity was 0. She's correct. My initial velocity was 9. My t is what I'm looking for. My acceleration is negative 1.8. And this is why I like physics.
Well, how did you get?
What? Tell me.
No, I'm trying to.
Okay. So
Okay.
here, I'm gonna algebraically do this, but you can also put this into the triangle if you wanted to. First step on algebra, you have a variable at the bottom. It can never be there. You can do the reciprocal over here, but you have to do the reciprocal over here if you want to do that, step 1. Or we can just go ahead and algebraically say, well, I need to multiply this side by t, that cancels out. Multiply this side by t. Okay, So I'm at 0 minus 9 equals negative 1.8 times t, right? Then I would have to get this side, divide by negative 1.8, cancel that out so that I can get t by itself, divide by negative 1.8, t comes out to, double check my math because this is last year's math. Actually, this is 2 years ago. I got 5 seconds 2 years ago. All right. But here is why I love physics, because the math is never wrong. T, which stands for time, can only be a positive number because time can only go forward. If I did my math correctly, I come out with a positive 5 seconds for t. Okay? Your math is not wrong. Your math is going to come out good. We can come back, but I think you can do example 1 on your own, but we can come back if you need help. Let's keep going because we don't have much more time. In a velocity versus time graph, okay, which is actually talks about the acceleration of an object, which is also called a VT graph. Remember the other one was a DT, this is the VT. Time is on the x-axis, velocity is on the y-axis. The slope of the VT graph equals the acceleration of the object. VT graphs, which, forgive me, that should say velocity. VT graphs. If I have an upward slope direct relationship line, that means that my object is accelerating. If I have a flat line, that means my object is moving at a constant speed. I'm not saying that it's not moving, it is moving, but it's moving at a constant speed. If I have another direct relationship line, it means that it is accelerating, and an inverse relationship line means that it is slowing down. But if you were driving, what's another word for slowing down? Brakes and decelerating. So you're braking, you're decelerating. Oops. So, 18, I can't even spell today. I-N-G. Can't even spell. Now we are going to break this apart a little bit more so that way we can tell if it's moving in a positive or negative direction on Friday. We've got 5 more minutes. It says here, calculate the acceleration of the 2 graphs below. So let's go ahead and do that. I'm going to say acceleration equals final velocity minus initial velocity over time. That's the equation. So let's look at this. This dot right here is my initial velocity. This dot over here is my final velocity.
0.
So my final velocity was 5. What is it? 5 minus 5 over how much time?
10.
10.
Or 5.
10. 10 seconds. Comes out to, I agree, 0 meters per second squared. Is it at rest, not moving? No, it is moving, but it's moving at a constant speed. It's not changing, it's not speeding up, it's not slowing down. It is moving though. It's not at rest. I'm going to go ahead and put that in parentheses, not at rest. Because I get students that see the number 0 and automatically think that it's not moving. That is not true. I don't have a direction. To Friday, though, I am going to be able to give you direction. And you will be able to put a direction here. Let's look at the next one. Here's my V sub I. Here's my V sub F. My V sub F I got was 32. Okay. My V sub I is 20. How much time occurred? 6 seconds. So I didn't
12 over 6.
12 over 6?
6. 30. 6 squared.
12 divided by 6 is 2 meters per second squared.
I was thinking of six.
Okay, other than that, I will leave you alone. I know it took the whole time, but we missed out on Monday, so we had to push through this whole
Are we
day.
doing example one?
Whoa, maybe
seven?
next week.
No,
But
we never did it, we skipped it.
I know we skipped it, but maybe next week. Tomorrow, I have to go over homework and I have to go over these two graphs. Bring your coloring stuff on Friday then. We'll have to color on Friday. DT versus VT graph. I'm going to show you direction then. Emily, you're running on your arm. What are you doing?